Volume of revolution. Consider the curve y equals f of x for x between a and b, as shown in the diagram just here. If the shaded part is rotated about the x-axis through 360 degrees, a three-dimensional shape will be formed. This solid is called a solid of revolution, and we can see that in the second diagram. The idea here is similar to area, in that we take an element, height of which is y, and a thickness of dx, and we rotate that around. Now, if you think about rotating that around, it's going to form a cylinder. And we can work out the area of that cylinder using pi y squared dx. Remember, when you have a cylinder, the volume is the area of the end, which is pi times the radius squared. In this case, the radius is y. And then you multiply by the length of the shape, which in this case is the thickness of dx. So that's the idea. I'm going to show you a couple of animations now that might make this clearer. So in this first animation, we have our disk already formed. You can see the curve going around behind the disk here. And so this is one of the disks. Now what you're going to do is have disks that go all the way from 0 through to the end of the curve here. And when you rotate all of those elements around, those disks are going to form a shape as shown. Now here's a second animation, and I can choose the number of elements I take here. So with 4, you see that I produce 4 cylinders, which would approximate the volume generated. As we increase the number of those, notice how, so we're seeing more and more of the elements over here, and notice how this is becoming a smoother curve. And when we get all the way up, this goes up to n equals 50, then we get a nice smooth curve. And so the area of all the cylinders formed by all of these elements would be very close to the volume of the solid generated over here. Now clearly, in the usual sense when we're doing infinitesimal calculus, what we're going to do is have an infinite number of infinitesimally thin disks, and that's where you get the dx. So we can use integration once we have that infinitesimal situation to find volumes of revolution between x equals a and x equals b, where f of x is non-negative in the interval. Since the volume of a cylinder is given by v equals pi r squared h, as we discussed, the volume of the solid of revolution is given by v is equal to pi times the integral from a to b of f of x squared dx. But this is usually written as v is equal to pi times the integral from a to b of y squared dx. Here, as I mentioned in an earlier example, we should really be saying x equals a and x equals b, because we've got y in here and we need to be clear that those are x limits.